Good morning, all. Is the slide visible? Am I audible?
Yes, sir. You're audible, sir.
Yes, sorry, no, I had to go step out for some 10-15 minutes. That's why I had to start a delayed class. It's okay. So let me not wait for others to join. About 35-40 of you are there, so I'll just be in. So yesterday you were looking at LSM, limit state method. For as of now we are looking at beams. So yesterday you went through what the basics of analysis using LSM is. Okay, so you also saw the differences between WSM and LSM in terms of how you find the balanced neutral axis. So in working stress method you say balanced. In limit state method you use the subscript U for ultimate. Okay. So it's minor differences between WSM and LSM. And you also saw on what basis you find the compressive force and the tensile force in limit state method. So the differences, instead of a triangular or linear stress block, you have a entire parabolic or non-linear stress block. So you find the centroid of that shape, you find the area of that shape, and you can get the total compressive force. You can also get the moment of ultimate moment of resistance. And the lever arm in limit state method for beams is nothing but D minus 0.4166 U. Okay, so these are things you will have to remember by heart. Okay, these are all very, very commonly used important equations. Okay, MUR equals 0.36 FCK B into XU into D minus 0.416 XU. Okay, so these are all very important things that you need to know. And in case you are if you're not able to remember this, you will find this code book in IS 456, design of beams. Okay, so that task is yours. You are encouraged to open up your code book and find out where these equations are present. And you also saw if it is under reinforced XU is less than XU max, and you can you will have to be able to estimate neutral axis depth by using this formula. And if it is over reinforced, you may have to do an iterative process where you take a mean of the calculated XU and XU max, and then using the strain what you have calculated based on the similar triangle. So using this, and by using this table in SP16, you can find out what the stress is, and using the stress you can go back to the equation on the previous slide and calculate what XU is. And if it's converged, you say that it is what to say, I mean that is your actual XU and your actual FST. Okay, so anyway, this procedures will become more clear when actually I wanted to do problems today on what was covered yesterday, so that it will be fresh in your memory. But since I started 14 minutes late, I decided let me do the problems next week, and today I'll just continue with theory itself. So the opposite of analysis is design. So in analysis, what you had is you will be given a size of a concrete beam, you will be given some reinforcement, grade of steel, grade of concrete, etc. And you will be asked to calculate, like, what is the ultimate moment of resistance, what is the stress in the steel, and things like that. So the opposite of that is design, where you will be given a beam, you will be given the length of the beam, you will have to calculate the moment, and for moment and shear, since it's a beam, and you will have to decide what should be the size of the beam, what should be the reinforcement, what should be the what grade of steel and what grade of concrete you can use in order to be able to withstand that load and that moment. So that is design. Both are counterparts. So first we will look at singly reinforced beams. Okay, singly reinforced means they have a reinforcement only near the bottom where there is tension. In general, when you do a design, whenever you do a design, you desire that your section should be balanced. Okay, you desire a balanced section, but in most cases, it is not possible to have an exactly balanced section because, for example, say that you have a concrete beam of size 300 by 500. So what is the condition for balanced section? What does it mean?
So the
what
K
happens
will
in
be
the
equal to KB.
yeah, okay. In terms of concrete and steel failure, what does the balance section mean?
So it means the failure will be balanced failure.
Yeah, or I mean the ultimate stresses in concrete and steel will be occurring at the same load. Okay, so that is balance section. And for example, if you have a 300 by 500 beam of a certain grade of concrete, and you use a certain grade of steel, you may end up calculating that to make the section balanced, you need, say, something like 1000 mm square of steel. Okay, but the problem with this is 1000 mm square. It is not always possible to give exactly 1000 mm square steel because your steel rods come in fixed sizes: 8 mm, 10 mm, 12 mm, 16 mm, 20 mm, 25 mm, 28 mm. Very heavy structures, you go up to 32 mm bars. So these sizes are fixed. So whether you, and it's, so whenever you give a bar, you can give an integer number of bars only, 1, 2, 3, 4, 5, 6. You can, just because you need 1000 mm square of steel, you cannot say that I want to use 5.5 bars or 5 1/4 of a bar. That and all cannot be done. So in many cases, you will not be able to actually provide the exact number of bars to reach that particular area of steel. So either you will have to give more than that or you have to give less than that. So if you give more than that, what type of a section is it? If you give lesser number of steel than what is for balanced, what type of a section is it? Simple question. More
So
area of
less it is
reinforcement.
under reinforced and
Huh?
less
Repeat
amount
it.
of steel is under reinforced and more amount of steel over.
It is over reinforced.
Lesser amount of steel will be under reinforced.
Yeah, that's right. Lesser amount of steel is under reinforced. If you give more than what is balanced, it is over reinforced. So in actual practice, it is only possible to do one of this most of the time. Okay, it's not possible to make it exactly balanced. So you have to choose whether to make it over reinforced or under reinforced. The recommended way is to make the beam under reinforced. Why is this preferred? Under reinforced rather than over reinforced?
So because tension failure is more favorable than compression failure.
Okay, correct. For what reason? Why is that more favorable?
Sir, because when
tension you can find, sir, like the visible cracks.
Ah.
But for the compression failure, it will like sudden. So
yeah, exactly. Very good. Very good. Very good. Yeah. So that is the main. So by the way, whenever if somebody answers, tell who you are, then answer so that everybody knows who's answering. That's also important in terms of participation. Anyway, so that's the right answer. So we always prefer under reinforced design for that particular reason. Okay. So specifications regarding length by depth of the beam, reinforcements. There are many specifications related to how to actually dimension your beam and how to arrange your reinforcement and all. So these specifications, they are there in the code book. They will be discussed a bit later. Okay. So design how you do is, so we say that no, XU max, which is the one for balanced, that is our target. Okay, we target XU max or a balance section. And that is our target, but you will not be able to achieve it. You will have to make it under reinforced. But anyway, when you start the design, you say that this is the maximum limit that you are allowed to reach XU max. So what you do is you will just rewrite the equation that you saw previously. Where can I? Probably I will go back to that slide. Yeah. You see an equation over here, right? This equation. What happened to this? So this equation. So this equation that you see over here. So what you want to do is you want to replace this XU with XU max. So what is XU max? XU max is nothing but either 0.53D or 0.48D or 0.46D, depending on what grade of steel that you have. So based on this, you just make that substitution, and also here as well. Okay, in both places. So you just make that substitution. Finally, your equation will be in terms of some constant FCK and D. Okay, you will get an equation like that, and that is what is this equation. That is what is this equation. So you just make the substitution, you get different equations for different rates of steel, and you call that as mu limit, meaning that it is the ultimate limiting moment, or that is the ultimate moment which a balanced section will take for that particular size of concrete beam and a given particular grade of steel. So based on this, if you are given a certain grade of steel, and if you want to make your beam to take a certain amount of bending moment, so you will just say that much bending moment you need to take. You will have to assume the breadth. Usually in concrete beam design, breadth B will be assumed, say that 300 or 350, or based on what the thickness of the wall beneath that beam is. Okay, so you will just assume a breadth. Grade of concrete you will know, and you will have to calculate what is the effective that is required. Okay, so setting mu limit equal to the calculated factored moment. What do you mean by factored moment? Discussed 2 classes ago. What is factor and what is factored moment? How do you get factor? Okay, how do you get factored load?
Multiplying with the factor of same.
Dividing by factor of same.
Yeah, based on what? Whether it's a single load or combination of gravity. So if it's a single load, what is the factor? Single gravity.
1.5.
Okay. If it is gravity load combined with lateral loads, what is the factor?
1.2.
1.2. So whatever that factor, you use that factor for the loads and then find the moment. That's it. That is Curtis factored moment. So for the factored moment, you will say that mu limit of the beam should be equal to at least this factored moment, and then you will be able to find out what depth is required. Okay. So then you will have your depth of the beam. And now the next thing is you have to find out how much reinforcement to give. So in general, you want to do balanced, you cannot achieve. So you will do a under reinforced design. So the equation in point number 4 can be used to get a quadratic equation in terms of the area of steel. So for the purpose of memory, let me shift back to equation number 4. This equation. So you would have found, the target moment which you want is this. Okay, you have found the factor moment, so you will just use that. Depth you would have just calculated in the previous step by using that mu limit is equal to 0.138 FCK BD square. Those 3 equations which I just showed you. So based on that, you will find out D. So that will also be known now. And the only unknown here is AST. Okay. So, and also of course, you will be using this equation and you can find out AST. So if you just substitute, so you can either you can use that equation and find out AST, or you can use that equation which I just showed you, and then you can, wherever you have XU, you can just replace it with XU is calculated as 0.36 FCKB by 0.87 Fy. So you just make that substitution and you will get the equation like this. Okay, this is just if you remember, you have 2 equations. M is equal to 0.36 FCK BD square into D minus 0.416 XU. That is one equation. And then in that equation for XU, you can make a substitution saying that XU equals 0.36 FCKB divided by 0.87 Fy, which is the equation that you use for initially assuming and finding out what is the neutral axis. So that equation. So these 2 equations you can just substitute and you'll be able to rearrange it and get an equation like this. So either you can have it like this, or if you find the root of this equation, you get this. Okay, so these are things which these equations are not present in the code book. So among this, whichever you find easy to remember, it's better to remember it. Of course, now everything is online exam, but in the days where everything was offline exam, one of these equations students will have to remember so that they can find out AST or PT. Okay, so just like you have a XU max for ensuring that the beam is balanced or under reinforced. Similarly, you also have a limiting percentage in terms of reinforcement. to ensure that the beam is under reinforced, because this is what is meant by under reinforced and over reinforced. You have a, if you give a certain percentage of steel, your beam is going to be balanced. If you go below it, it's under reinforced. If you go above it, it's over reinforced. So therefore, in order to ensure that your beam is under reinforced, corresponding to the balance section, you have a percentage of steel. Okay, so this percentage of steel is also constant for any given grade of steel, and it is given as for Fe250, the limiting percentage of steel is 0.0884 FCK. For Fe415, it is 0.048, and for Fe500, it is 0.0379. That's a zero missing over here. I'm sorry. Okay, FCK. Okay, so when you do your design, once you estimate what is the percentage of steel that is required, just check with this limit and ensure that you are below that limit, the steel which you have given. So now, before I go to the next slide, I want to ask a question. Let's say that you have done your design, you have found the depth of your beam. You have also found out what is the percentage of steel that is required, the tension bottom steel which is required. And then you make this check and you find that the percentage of steel is more than this limiting percentage. That means it is what kind of beam?
Over reinforced.
Okay, it becomes over reinforced and you don't want it to be over reinforced. Now, what is the now you have two options. One is reduce the steel. Okay. So you require a certain amount of steel to take the tension. But if you reduce the steel, what will happen? Just because it's over reinforced and you don't want it to be over reinforced, if you decide that let me reduce the steel which I am giving, is it okay or is it a problem?
It's a problem, sir.
It's a problem. Yes, correct. Why?
Sir, we want it to take some load, and if we are reducing the steel, then it won't be able to take that load.
Yeah, exactly. So because you are giving a certain amount of steel to take the particular moment. Okay, that particular moment causes a tension on the bottom. It is for that particular reason only you are giving this much of steel. So if you reduce the steel, that much moment won't be taken. Your beam will fail before that moment is reached. Okay, so that is also not a good idea to overcome this over reinforced problem. What is the other thing that you can do in order to make it?
The dimensions of.
Very good. You can increase the dimensions of the beam, or you can increase the area of the concrete that is there. That will ensure that because if you look at your equation, okay, if you look, best thing is I just go back. So if you look at this equation, if you look at this equation, if you have a look over here, you see that in terms of neutral axis, you see that if your area of the beam is increased, okay, or B is increased, if you increase the area of your beam, usually nobody will increase the width, people usually try to increase the depth. So when you increase it, you see that your XU will become lesser. Okay, XU becomes lesser, meaning that XU goes up, or it goes into the under reinforced range. Similarly speaking, when you talk in terms of percentage of steel, percentage of steel is given as the area of steel divided by the area of the beam, concrete beam. So if you increase the usual way is to increase the effective depth of the beam D. So when you increase this thing increases and your percentage of steel comes down for the same area of steel. So that is the thing which you need to do. This is one of the solutions. And there's some more, and there will be some instances where the architect or the design people will say, no matter what, we cannot allow you to increase the depth of the beam because of space, aesthetics, and all those reasons. So you will encounter a lot of situations where your percentage of steel you cannot reduce. The area of steel you cannot reduce. Depth of the beam also you cannot reduce. So there's a solution for it, which will be coming up shortly. So before I go to that solution, let me just stick with singly reinforced beam and say what the limitations are. As I told you many times, there are restrictions placed on the beam depth due to floor clearance requirements for functional or architectural reasons. So many times you cannot, you will not be allowed to increase the depth of the beam as you wish. Okay, for example, this is a ramp coming out of a parking lot. So somebody cannot just keep increasing the depth of this beam because slightly larger vehicles will get bumped onto it. So this is just one instance of why sometimes restrictions are placed. In such cases, if the required depth is greater than the stipulated, what can you do? Okay, so lesser depth means lesser proportion of area of concrete by steel, meaning that the proportion of steel within that area will be more. Okay, and if based on this required, if you base your if based on this required moment and depth, if you provide the steel which is required, then you will find a situation where you will be in, it will be in over-reinforced situation. Actually, I gave a question mark because I wanted to ask you what will it be, but anyway, I think you people will be capable of answering it now. So yeah, so when you limit your depth and you want to make it designed for that particular moment, then you will end up being an under-reinforced beam. And of course, bottom only steel is there. No matter how much ever steel you give, on the top, if you don't increase the depth, concrete will get crushed. So the solution is these things. One easy solution is increase the grade of concrete. So for example, if it is M20, M25, you make it M30 or M35C see if you're able to adjust with the same depth. Okay. But what if the concrete is already of a normally high grade such as M35 or M40? Okay. So that is one solution, but usually the contractors will not accept for just one particular area. Nobody will want to increase the grade of concrete. Just for example, just one particular beam in a whole big structure or one particular column. It is always advisable to use the same grade of concrete. Making one structure with different grades of concrete for different parts is also not a good idea. And the next solution is, can you increase the breadth of the beam? Okay. Now say moment resist. What I can say is, for example, when you the bending stress. Okay, bending stress or bending strength. Now, how do you find bending stress or bending strength? Strength of materials approach, mechanics of solids. How do you find bending stress? Formula.
Sir, M by I equal to sigma by Y.
M by I equals sigma by Y, or M equals sigma I by Y. Correct? Yes. Sigma I by Y. Okay. Now, what does I depend on?
The cross section.
Breadth and depth.
Breadth and depth. Which does it depend on more? Does it depend more on breadth or more on depth?
Depends on the
depth.
On the
depth, sir.
Depth by what order?
Order of 3.
Order of 3. Okay. So if you want to increase the moment of resistance, what do you prefer increasing, breadth or depth?
Depth.
Depth. You want to increase the depth because that will give you a great range. So increasing the breadth is not very effective. Okay, you will have to give a very long breadth, which is useless, to be very simple. So increasing the depth is the only solution. Increasing the breadth does not help much. And increasing the depth, people are not allowing for certain reasons. So what do you do? Okay. So there comes your solution, something known as doubly reinforced beams. Okay. So you need a sufficient moment of resistance for resisting the applied load, but the depth and lever arm are limited. Okay, because of reasons stated previously. With the given grade of concrete, only solution is to increase the internal resisting force. Okay, compression or the tension. For example, when your depth is fixed, the depth of if your depth of a beam is fixed, D minus 0.416 XU, which is the lever arm, that will be fixed. Okay, and your moment of resistance is nothing but compressive force times lever arm. Okay, times of the lever arm will give you what the moment of resistance is. So if your depth is fixed, then more or less lever arm will not change too much. So for that reason, one of the ways to solve this problem is to increase the internal resisting force. So how to increase the internal resisting force if the grade of concrete and beam cross section area are fixed? Okay, so there's a workaround to this. So just calculate how much area of tension reinforcement, the bottom reinforcement, no? Calculate how much is required. It may make this beam over reinforced. Okay, but whatever it is, just provide, for example, even if your area of steel which you require for this moment, even if it is coming more than the area of steel for a under reinforced or a balanced failure, even then go ahead and provide that tension reinforcement. So once you do that, it will make the beam over reinforced and the neutral axis will go a bit down. It will shift a bit down, and this will increase the compressive force, because when your neutral axis shifts down, the area of that parabola will become bigger and the compressive force will increase. Okay, and since the reinforcement is also high, your tension will be high and it will be equal to C since the reinforcement is high. But of course, this is an over reinforced beam, and therefore whatever problems are there with an over reinforced beam, they will still be there. For example, the concrete will crush for this value of C, while the steel will not have yielded. Okay, and this has to be somehow prevented. You have to prevent the concrete from crushing. How is that done? So a very simple, elegant solution for this is, see, you know that in over reinforced beam, the failure is going to happen by crushing of the concrete on the top. So what engineering solution is, let us ensure that the concrete on the top has some help, okay, in taking the compressive force, and therefore something known as a compression reinforcement is provided, meaning tension reinforcement is given usually for simply supported beams, it is given on the bottom. This compression reinforcement will be given on the top, as close to the top surface of the beam as possible. Okay, and of course this compression reinforcement is inside the beam. It is surrounded by concrete and it is packed. So therefore there will not be any buckling in the reinforcement, or no such issues will be there. So this is the way to actually address this. So to give a very simple to tell you how this works through a very non-engineering example. So there's a kind of a game or competition where there will be a rope, center of the rope will be known, and from two sides, two groups of people will try to pull the rope. Okay, so have you people seen this kind of a affair, a competition?
Yes.
So what is that competition named as?
Tug of war.
Tug of war. Okay. So you have a tug of war competition between two groups on this side. So most of you should know who these groups are. So one side is this and another side is this. Now, based on your opinion, which side do you think the rope is going to be pulled? Any answer is acceptable. So, I mean, anybody who follows these things can answer. No, which side do you think the rope is going to move? Towards this side or towards this side? In a tug of war between these two groups.
Left.
To the left. Okay. Anybody disagrees or everybody agrees with the left? Okay, I also go with the left.
It will not move.
It will not move. Okay, for the purpose of this example, let me agree with the person who answered before and say that probably this side is more powerful and this is going to try to move to the left. Now the target is we don't want this to move either to left or to right. Okay, so if this tends to move to the left because this group is more powerful, so if this has to be kept at the center, what should be done? Where is help needed if this has to stay at the center?
Right.
Right.
So you need an additional help at the right to restore equilibrium or to keep it balanced. Okay, if you go by concrete terminology itself, to keep it balanced, you need additional reinforcement on the side. Okay, additional reinforcement, and if you give additional reinforcement, then probably it is going to get balanced and this side will not be crushed. Okay, so this is basically the very simple reason or the idea behind the double reinforcement. So you want a balanced position. You want to avoid compression failure on the top from an over reinforced beam, and therefore you add reinforcement on the top. This is why I actually gave male stars on this side and female stars on this side, because I wanted to differentiate between steel and concrete. Okay, and steel area is always very less, but it's stronger, so that's why I kept 2. Concrete area will always be more, but it is weaker. Okay, so that's why I kept 3 here and female superstars. I'm not going into anything political regarding gender thing and all, but anyway, just a colloquial example. And since reinforcement I have kept male stars, I've given another reinforcement rod to differentiate between steel and concrete. Okay, no other discriminatory reasons over here for this kind of pictures. This compression reinforcement, these are tension reinforcement, and Wonder Woman and Co are concrete. Okay, so the analysis of doubly reinforced beams is very similar to the analysis of over reinforced beams. Okay, so beams that have compression reinforcement near the top 2 are known as doubly reinforced beams. Reinforcement is provided in the compression zone to assist the concrete in keeping up the forces resisted by the tension reinforcement. This changes what would have been an over reinforced beam into a under reinforced or balanced beam. So once you make it a doubly reinforced beam, the concrete will not, the target is the concrete should not fail in compression on the top. Okay, and you are once again trying to make sure the failure is going to happen on the bottom, tension reinforcement. So what should have been an over reinforced beam changes into a under reinforced or a balanced beam. So this is what in general, in addition to the normal stress block which you had for singly reinforced beams, you have another component known as CS, or the compression force from the steel on the top. Okay, so you have an additional force which balances out this value which is high. So the total compression force in the concrete is the 0.36 FCKB into XU plus the stress in this steel times the area of the steel. Okay. Of course, you have given some the reinforcement which you've given on the top. It will replace a small area of concrete on the top. So you just subtract that area of concrete. Then the force in the tension steel will be, if it is, it will mostly be, once you make it under reinforced steel, it will become 0.87 Fy. And if you do not give commensurate number of steel on the top, it will be some other value of stress. The line of action of compression in steel is at the level of top bar. So it's at this level, wherever you've given the bar on the top, that is where the compression force from steel will act. The steel in the compression, see, always the steel in the bottom mostly will be 0.87 Fy. But the steel on top over here, it need not be 0.87 Fy. It may be something lesser than that usually. Only the steel on the bottom will usually be 0.87 Fy. So the stress of the steel on the top is not known, and you need to find it out by using a procedure very similar to the one which was explained for over reinforced beam. So a similar triangle equation used to find out what the strain in the top steel is. D is effective depth. D dash is the depth from the top of the beam to the just below the steel which is there. So that is D dash. Okay. So use the same interpolation procedure as before. Find out if XU is less than XU max. And then actually basically this is the same procedure, like we don't spend too much time explaining it. And using that we'll find out what is the strain in the compression steel, stress in the compression steel, in addition to those in the tension steel. So now you will have just a slight change in the formula for XU. So previously for singly reinforced beam, your XU formula is nothing but FST AST divided by 0.362 FCKB. If you have a doubly reinforced beam, it slightly changes. It becomes FST AST minus FSC minus 0.446 FCK into. So this is basically the compression steel part. This part is basically the concrete which has been replaced by steel on the top. Okay, so you just account for that and then divided by 0.362 FCKB. Okay, just basically this. So this is neutral axis, this is D minus D dash, and your ultimate moment of resistance will have this CS component also coming into the picture. So your moment of resistance becomes 0.362 FCKB D into D minus 0.416 XU, which you already know, plus this other part, which is given by this lever arm. Okay, from the compression steel to the bottom tension steel. And just like PT limit in under reinforced beams, which says that you should give lesser than this percentage of steel in the bottom, there's a PC limit or compression steel limit which says that this is the minimum compression steel which you need to provide to keep the beam under reinforced or to prevent the compression of prevent the concrete from cracking in compression before the steel yields. Now PT limit says you should not cross that limit. You should not give more steel than the PT limit. Now PC limit, what kind of a limit do you think it is? Is it a minimum limit saying that you should give at least this much limit of steel, or is it a maximum limit which says that you should give lesser than this limit of steel? For PT limit it says don't cross it. For PC limit, what do you think? Should you give more than that or less than that for compression steel? Go back to the tug of war. If it needs to be balanced, is it enough if somebody who's not good enough to help, just one person he comes, it will be enough, or you need someone to at least make up for that difference? So is this a maximum limit or a minimum limit? Should you cross it or should you not cross it? PC limit. PC limit is the percentage of steel which you need to give here on the top for doubly reinforced beam. Minimum, meaning that it should be more or less. The steel should be more than that. It should be.
It should be more.
Should be more. Okay, you should give at least that much compression steel on the top to make sure that it is under reinforced and doubly reinforced. Okay, so this is the procedure. Next class we'll do a few problems on design. Let me not do now. Next class we'll do 3 problems of analysis of singly reinforced beam, under reinforced, over reinforced beam, and a doubly reinforced beam. So 3 problems we'll do in the next week's class. Till then, please open your codebook IS456 till next Wednesday. Your task is open IS456 and how much time is left? Oh, 12:26. Okay. Open the contents page. Okay, go to limit state of collapse, go to beams. Okay, open that. See the contents page, table of contents, see where is limit state of collapse, and within limit states of collapse, see where the classes with respect to beams are. And please go through those provisions. You will find a lot of things which were discussed in today's class. Okay, so that is your task for the weekend. So with this I'll stop. You also have another class. I also have another class. Stop recording.